Next paper is also from Alibaba, but we have, first of all, we're lucky to have a presenter in person. Also, we have, for change, a senior person. So Yunfei Ma got his bachelor's from USTC, then PhD from Cornell. He was a postdoc at MIT Media Lab before moving to Alibaba. And I'm not going to repeat his long CV. He published probably a dozen or so papers at top conferences. He was on the program committees. And also, he got some quite an amount of media coverage as well about his research.
OK, hello, everyone. I think I have the privilege to be the last speaker of the last session at this year's SIGCOMM'. And in this talk, I will speak on a group of my fantastic co-authors. And I will present GSO-Simulcast, our new video conference architecture that is in Alibaba's DingTalk. And for the rest of the talk, I will explain why we designed GSO, the technical challenges particular, and we need to overcome to make GSO reality, and also the benefit we saw after deployment. So video conferencing is really an exciting topic and exciting area. And more importantly, it has really been essential to our society now, and it has fundamentally reshaped the society, and is now really the beating heart of the remote collaboration, learning, and personal interaction for billions of people around the globe. And also, over the last couple of years, and we have also witnessed the commercial success of many video conferencing apps, such as Zoom, Microsoft Teams, and including Alibaba DingTalk. And for the DingTalk, our video conference service has increased 100 times during the COVID pandemic period. And currently, we are the largest remote collaboration app in China, which currently serves more than 500 million users. So the story for us is, as the app becomes more and more popular at the beginning of 2020, it's always nothing is more important to deliver satisfactory user experience to our customer, because we are a customer-first company. And but getting good user experience is really a challenge. As you can see here, what I show is a summary of user-reported issues, and there are a number of things we need to work on the list. And the top 3 issues are video stalls, voice stalls, and video picture blurry. So why video conferencing is hard? There is a fundamental reason. That is that in a multi-party video conferencing, you have this heterogeneous network condition. And I will explain to you what I mean by that. So basically, different people in a multi-party video conferencing, they see different network conditions. And in this particular example, I have 1 publisher, PUB1, and 3 subscribers. And the PUB1 has an uplink bandwidth of 2 megabits per second, and the 3 subscribers has 2 megabits, 1 megabit, and 500 kilobits per second bandwidth in the downlink, respectively. And so a natural question arises: what bitrate should the publisher send in this scenario? And as you can see, if I choose to push a 2 megabits per second stream, it will serve subscriber 1 best. But in doing so, it will cause congestion at sub-2 and sub-3 because their network bandwidth cannot sustain such a high bitrate. And as a result, what publisher 1 can do is to publish a video stream that is less than 500 kilobits per second, but this inevitably hurts the performance of sub-1 and sub-2. And as a consequence, in a multi-party video conference scenario, the performance is bottlenecked by the client who has the slowest link. And also, with more and more people join the conference, the likelihood of the slow link increases with the number of participants. And we must address this slow link problem in order to get any satisfactory user experience. And one solution to alleviate this problem is Simulcast. In Simulcast, a client encodes a video source multiple times and sends those streams in parallel to an SFU server, and the SFU server then decides what to switch and forward based on the downlink bandwidth condition. And in this particular example, again, it chooses to send the high bitrate stream to sub-1, the medium bitrate stream to sub-2, and the small bitrate stream to sub-3. And in order to get Simulcast to work, the first thing you need to figure out is the right stream policy. And the stream policy answers 2 questions. The number 1, how many streams should the publisher send? And number 2, at what bitrate should the stream be set to? In other words, you really need to have the right number of streams at the right number of bitrate. Otherwise, simulcast does not work and cannot give what you want in the first place. And before I jump into the GSO, I will first talk about how the stream policy is implemented today. So what I show here is the stream policy used by AWS Chime, and this information is public. And as you can see in this table, from left to right, the first two columns are the number of participants in a meeting and also their local uplink bandwidth constraint. So what you really do in this scenario is based on how many people you have in a meeting and also your local uplink bandwidth measurement, and you look up in this empirical table and decide what to publish. And there are a number of constraints in this policy. The first one is the upstream policy are isolated from the downlink demands and downlink bandwidth constraint. And this can lead to, for example, sending unnecessary video streams that not only waste bandwidth, but also cause uplink congestion. And the second thing is today's simulcast typically support coarse grain bit rate levels, and with just a 2 to 3 bit rate levels, it's really difficult for you to perfectly feed the video to network, and it will cause video and network mismatch. And the third thing is that the empirical policy is very difficult to manage and to scale to a lot of participants in a meeting. For example, in the AWS Chime case, they do not differentiate beyond 6 people. However, in today's meeting, it's quite common to have 100 or even 1,000 participants. And so generating a good empirical policy is really difficult. It's really a challenge because you can't enumerate every cases. And therefore, we decided to build the GSO-Simulcast. So note that the fundamental flaw in today's simulcast is, first, is video adaptation is done locally, and also it's done based on a local view of the network. And instead, what you really want to have is to have the global stream orchestration based on the holistic view of the network in a meeting. And so here is a simplified overall architecture, and we split the meeting into 3 planes. The down there is a user plane. It is formed by clients who play the role of subscriber and publisher. And above that is a medium plane to provide access to the users. And at the top is a control plane. It consists of 2 nodes, the conference node and the GSO controller. The conference node has 2 main functions. First, it handles signaling, and second, it captures the complete picture of a meeting, including the subscription relationship, the bandwidth constraints, and also the codec capability for each participant. And this type of information are then used as input for the GSO controller, which acts as the brain of the conference. And then the GSO controller will solve the global optimization problem with the goal to maximize the overall QE utility of the users in the user plane. And in GSO, we currently support fine-grained bit rate levels. We can support to up to 15 discrete levels. And also, the stream policy is automated, which makes it easier to scale to even 1,000 participants. And so what benefit can you get from GSO? Here, I will illustrate through a couple of simplified examples, but note that in reality, the application scenarios are much more complex. And in the first example, I have 1 publisher who publishes 3 streams to the SFU server and 2 subscribers. And sub 1 and sub 2, they only want to subscribe to a medium bitrate flow and a small bitrate flow. So this high bitrate flow, 1.5 megabits per second, is unneeded. However, in traditional simulcast, the downlink stream policy is isolated from the downlink so that the publisher is not aware of this situation. So this stream is still pushed up, which not only wastes bandwidth, but also more likely to cause congestion in the uplink. And with GSO, since it can get improved, GSO has a global view so that it will instruct the publisher to just send what is needed. And with this, we not only save bandwidth, but also reduce the likelihood of uplink congestion. And in the second example, the publisher 1 still publishes 3 streams. And in this case, the downlink subscriber has a downlink constraint, which is slightly below the high bitrate stream the pub 1 sent. And in this case, the SFU has to forward the 600 kilobits per second stream to the subscriber. And due to the coarse-grained bitrate levels, this leads to poor network utility and also cause video and network mismatch. And with GSO, since it gets improved, first we implement fine-grained stream policy. Next, the GSO is aware of the downlink bandwidth so that it will be very precise. It will tell the sub-publisher to publish a 1.4 megabits per second stream, and so that the downlink utilization rate is improved. And this can also help us to reduce network and video mismatch. And in the third example, we have two publishers, and they each publish 3 streams. And the subscriber wants to subscribe 2 high bit rate streams from PUB1 and PUB2, but his downlink bandwidth is also limited. So this uncoordinated local view leads to stream competition in traditional simulcast. And what ends up happening is he gets a high bit rate stream from PUB1, but a small bit rate stream from PUB2. So the downlink bandwidth is unevenly distributed between the 2 publishers. And with GSO, the situation can be improved. And GSO has a global view, so it is aware of the stream competition, and it will instruct both publishers to send a 1 megabit per second stream to share the downlink bandwidth evenly. And with this, it can help us resolve stream competition. The next question is, how do you actually build GSO? It turns out that building GSO is non-trivial. There are a number of questions we need to answer. The first one is, how do you correctly model a conference? Because without a correct model, you cannot go on to do the optimization. And this model also needs to include many practical constraints. And the second one is, we need the control algorithm to be done in real time. But the problem is combinatorial in nature. The third thing is, we want to have a mechanism so that we can capture the global picture of the conference. And then we also need a real-time feedback mechanism so that the clients in the user plane can react to our policy in a very fast manner. And here is how we model the conference. We have 4 types of constraint. The first constraint is the subscription relationship. And in this constraint, the clients will indicate the maximized resolution he's willing to accept, and there is no overfitting allowed. And for the next constraint is the codec capability constraint, and it determines the supported resolution and the available bitrate of each particular participant in the meeting. And in GSO, a publisher can publish multiple streams in different resolutions in parallel, but for each resolution, only 1 bitrate can be set at one time. And the third and the fourth constraint are the bandwidth constraint, and it is relatively easy to understand. So for the uplink bandwidth constraint, we require that the summation of all upstreams to be no larger than the uplink bandwidth. And in the downlink, we require that the summation of all downstreams should be no larger than the downlink bandwidth. And it turns out that here, the problem is this optimization is combinatorial in nature, and hence the time complexity of brute force searching grows exponentially with the number of participants and also bitrate options. And here, one of the key enablers of GSO is the real-time control algorithm. And here, what I show here is a sketch of the algorithm. But for the sake of time, I will not go into too much details about the algorithm. I will only talk about some high-level intuition. So basically, what we are trying to do is to find a good approximation that is computed in pseudo-polynomial time with an innovative iterative knapsack merge reduction algorithm. But I do encourage you to read our paper for more technical details here. And the next thing is how do you capture the global picture of the conference? As I just mentioned, there are 4 types of constraints. And for the subscription info, is automatically handled by the conference node, so we do not need to do too much change here. And for the codec capability, we need to append simulcast info message to the SDP offer when a client joins the meeting. And in the downlink bandwidth, the bandwidth is estimated on the SFU server, so there is also not too much change to be done here. But the problem is the uplink bandwidth, and in GSO, all bandwidth estimation are done at the sender side. So the bandwidth information is disaggregated. And what we do here is we define an SEMB format in the RTCP packet so that this can be done in the in-band manner. And the next thing is, once we compute the solution, we also need to send a feedback to the client so that they can react to our policy. And we also need this to be done in a very fast manner, so we choose an in-band feedback mechanism. And in particular, what we use is a TMMBR message in RTCP to notify the client about stream configuration. And once the client change their codec, they will send an ACK with an TMBN message. Because we can compute the solution in real time, and also we can send the feedback in real time, so here we can see that we have a very good bandwidth adaptability. So what I show here is a transient response comparison between non-GSO-Simulcast and GSO-Simulcast. So in these two figures, the x-axis is a time, and the y-axis is a bit rate. And in the experiment, the bandwidth is limited to different bit rates, which are indicated by different colors. As you can see, the GSO can react to bandwidth changes in a very fast manner. And also, what you also can see is the benefit of using fine-grained bit rate levels. And in each of the cases, the bit rate is just right under the bandwidth limitation. And in comparison, for the non-GSO simulcast, it cannot have such a high bandwidth utilization due to the coarse-grained bit rate levels. And for next, I will present the deployment results. And we started the deployment at November 20th, 2021, and reached a full-scale deployment at December 20th, 2021. What I show here is a statistic result that is sampled from 1 million conferences per day, and the total data set consists of over 100 million conferences. And also here's our definition of video stall and voice stall for the online data. And what I show here is the normalized video stall, voice stall, and frame rate versus the date. As you can see, with the deployment of GSO, all three key metrics get improved. And also, one interesting thing to notice here is that with the development scale of the GSO, the performance is getting better. And in the end, compare the result after deployment to the result before the deployment, the video stall, voice stall, and the frame rate are improved by 35%, 50%, and 6% respectively. And what's more important is the normalized user satisfaction score. And this score is calculated as the percentage of users' positive feedback. And here's the result. So as you can see that we also see improvement in user satisfaction score with the deployment of GSO. And the overall satisfaction score is improved by 7%, which is also significant for a large-scale video conference. And so for the conclusion, in this talk, I present the GSO-Simulcast in our DIN Talk video conference service. And with the deployment, we observed significant improvement in all key metrics. And we also discuss more of our experience in our paper. And if you are interested, please take a look. Thank you so much, and thank you for your attention.
Maybe Sanjay was first, and Henning after.
So in your, what you do is have the publisher upload multiple qualities to the central server. So the producer uploads different qualities, correct? So
yeah, that's simulcast, yeah.
So I would, since the producer's uplink is likely to be the bottleneck, why not just upload one quality and then have some transcoding at the central server?
Yeah, that's actually a good question. Yeah, so basically, at the beginning, the first thing we try is transcoding. Yeah, but then we figure out that transcoding is also a lot of cost for us.
Okay.
Yeah, because we are the service provider, so if we do the transcoding, you need to decode and re-encode the video, right? So that is a major cost.
Okay, and do you do any multicast, or so when all the receivers who get the same quality, do you just do unicast to all of them?
We do unicast.
Okay, thank you.
Thank you for a very interesting talk. One adaptation that I didn't see is when doing video conferences, you have, in many cases, the receivers have basically an automated focus on acoustic speaker, yeah. As in the video gets much larger when you speak and goes to postage stamp size when you are just sitting and listening. How do you that can obviously happen very rapidly, every few seconds, really. Do you adjust for that, or when somebody switches, like you had this equal allocation between bandwidth, or you each one wanted to give them the same bandwidth, but if one is the speaker and one is just a listener, that's the wrong assignment, so to say. You want the speaker to get almost all the bandwidth, and you can show a photo of the non-speaker and nobody will mind.
Yeah. That's actually a very, very, very good question. So in fact, if you think about the configuration is computed with a global optimization, and for that you can basically what we do is for important like video stream where we assign a high QE value, and so that they get protected. And so basically, if you have two persons with the same QE value, and what you want is you want them to share the bandwidth evenly. But for example, if you are the speaker, I just want to listen to you, right? And then you will have a very high QE value, so that we ensure that this stream gets prioritized in the algorithm.
Yeah, just a quick follow-up to the previous one. Are you using SVC or just whatever MP4 streams?
Yes, that's a good question. SVC, we see the trend, and also yesterday I talked to Oliver, and he also has a very interesting observation. And currently at our Ding Talk, we do not use SVC for a couple of reasons. The first reason is that we want to use hardware codec. And some of the H.264, they do not support SVC because it is in the extension of the standard. And the other part is that for SVC, that's our philosophy. For SVC, because you have this layered encoding, so for the same quality, you need to spend more bits on the stream. But what we have is a large fan-out scenario where one stream you push to the server and it gets to send to like 50 people or 100 people. So if you increase the redundancy for that stream, and then the bandwidth cost gets amplified in the downlink. So that's also a cost factor for us.
So Hyung-ho, quick question.
I wonder how GSO-Simulcast determines the granularity of the bitrate in the ingest path, because it seems that GSO-Simulcast support a fine-grained bitrate. I mean, the supports, but some cases maybe 100K difference might not seem bigger, so it can be some kind of resource waste in some case of videos, but some case of video maybe 100K might be meaningful. So how does GSO-Simulcast determine such granularity?
Okay, that's also a great question. So basically, the way is so basically what you do is you have this simulcast info, right? And it will convey the message to tell me, right? Before that, you need SDP, right? Before the video call is established. So different codecs may have different capability. So for example, some codec they can support, they are willing to support more bitrate levels, but some may not, and you need to consider that. And also, so for us, if you have the capability to support a fine-grained bitrate level, so we basically we have this table, and we also show that in the paper. So basically, what type of bitrate correspond to what type of QE value. And based on the Q value, we determine, okay, what is like the granularity we want to have.
Okay, so the kind of the QE model is the generic over the multiple streams. Yeah.
Can you repeat this?
So you mentioned about the QE model that maps
QE model. Yeah, we have a table. You can look at that table.
Thank you.
Let me conclude the QA with another not entirely technical question for Alibaba paper. So looking at your paper, actually, you have more mathematical modeling and analysis that I've seen in most of the academic papers in SIGCOMM'. So what does that mean? That I know Alibaba develops and deploys systems based on solid theory?
Oh, okay. That's a good question. I think our paper is really in a different flavor. because one thing is that first we think that this video conferencing is very interesting and it's also very important. And you can also see we have also followed a lot of past work which is done by Henning. And the thing is, but also we also see the other side. Like recently, not too many paper that is published in this video conference topics. And now, because of after the COVID-19, everybody thinks that okay, video conference is getting more and more important. So that we also want to clearly explain, right? So why we can enable this. Otherwise, when we have this paper, we ask for some feedback, and people say, oh, they don't have the context of message of right. In this paper, so that we in this one, because we think that the key enabler, right, is really, if I just tell you, okay, we want to do centralized control, you don't know why, what's going on, right, and what are the challenges, why this is so difficult. So we want to also write that theory down in this paper. But in addition to that, we also have a lot of experience and measurement for the rest of the paper.
Okay, thank you, Yunfei, for the presentation. And let's conclude question here. So we have put 3 Amsterdam crosses for the 3 in-person presentations. We got 5 crosses for all the 5 presentations in the session. So let's again thank all the presenters: Chizhe, Xie Shong, Hyun Ho, Jin Yang, and Yunfei. So let's give another round of applause. And doesn't complete the show, so Fernando was pacing nervously because I didn't fulfill my promise to be on time. But yes, now there is another round of announcements by organizers.